Next time we're going to talk about anomaly detection, and in doing so we're going to talk about methods like mixtures of Gaussians and the EM algorithm. But this time we're going to cover kind of basic unsupervised learning algorithms. And in particular, as I'll talk about in a second, we're going to cover the k-means algorithm and the PCA algorithm. So I guess before I begin, is there anyone in this room who's doing their tutorial on one of those two things who has not yet submitted it? Okay, good. This is sort of the exception where, unfortunately, it was originally due today, and so it wasn't that big a deal. But if you're doing this for your tutorial, you can't be in this class, so shouldn't be in this lecture at least. But fortunately, no one's in that situation. It's a little bit unfortunate because the deadlines moved, so we had to. They get less days than everyone else, but that is too bad. All right, so in particular, we're going to cover a general framework for unsupervised learning. So to start off, I'm going to phrase unsupervised learning in a way that's actually fairly similar to how we talked about supervised learning, which is a little bit different from how it's normally presented. Normally, the unsupervised learning algorithms, I think, tend to be kind of thrown out one at a time. So you have something like k-means, which is a clustering algorithm. People learn about that. And they learn about PCA, which is a dimensionality reduction algorithm, which seems to be something entirely different, right? It looks like it's a different kind of geometry, different types of methods are being used. It seems completely different. But just like with supervised learning, it turns out that a lot of unsupervised tasks, unsupervised algorithms rather, all belong to this same class of methods. In other words, you have to specify, just like with supervised learning, a hypothesis function, a loss function, and a way of optimizing your loss function. So it actually ends up being something very, very similar to the process of defining an unsupervised learning algorithm. But we'll talk about that. Then we'll talk about, in particular, k-means and PCA. Oh, I misspelled principal right there. That's odd. It wasn't in most slides. It's principal typo. Let me fix. Well, I won't fix it now. I'll fix it in the later ones. I was actually just thinking about that typo before I did it, but it's P-A-L, principal, not principal. Not like the principle of the thing. What was that? I know. It's awful. All right. Well, I'll fix it. But it's all I think it's just my outline slide, sadly enough. OK, so first of all, some quick announcements. As I'm sure everyone's aware, the tutorial is due on Wednesday. And you can use at most 2 late days. The reason for that is we want to distribute them back so that everyone can grade their own tutorials without that overlapping too much with the homework, or grade other people's tutorials without overlapping too much with the homework. So we're making you use at most 2 late days. So it's going to be due at most Friday at 12 p.m. I also sent some feedback over the weekend. So I think I commented on everyone's whose format I could read. There were a handful of people whose notebooks I couldn't read. So you got that feedback, that I couldn't read your notebook. These are just suggestions. So it's obviously getting fairly close to deadline. You're welcome to incorporate them, but you don't have to. It's suggestions. You don't actually need to incorporate them. So if you want to, by all means, that's great. Otherwise, write what you think makes the best tutorial. OK, any questions about sort of logistic stuff going on right now? Yeah.
So I was, in my tutorial feedback, there was a suggestion of, oh, you should compare this with this library. Mm-hmm. And I haven't. Is that, so it's not, it was just a suggestion?
It's a suggestion. It's suggestions to think that things that I thought would make these things good, but they were brief. And if you feel like it does not actually make your thing better, go hell. So if it was already perfect, then I just had to say something. So I was scraping the bottom of the barrel, clearly. All right, any other questions? OK, so let's jump into unsupervised learning. And I want to set up unsupervised learning. I think most people here are probably familiar with at least, or have heard about things like clustering or k-means before. But I want to take a step back and talk about unsupervised learning in general. So when we talked so far about machine learning, we've talked really about the supervised learning setting. And that's the setting. That's a setting where we have as our training data pairs x and y, where x is our input and y is the thing we want to predict. Right? That seems kind of straightforward. We fed this into a hypothesis function that would try to predict something that's close to y given x. And then we would apply the same hypothesis. And the sort of training process there was the process of building this hypothesis function, or finding the parameters for the hypothesis function. And then when we had a new example, we would take our hypothesis function and apply that to the new example and get our prediction on that new example. So that was our supervised learning pipeline. And so now we go to the unsupervised case. And as the name kind of suggests, in the unsupervised case, even in the training data itself, we don't have any outputs. So these disappear. And we now have just a bunch of x's, just inputs, right? And here we're going to think of them, or I'll define them in a second, but they're going to be in Rn, just like they were before. So we'll think of them as vectors in n-dimensional space. So now the question is, what's going on at this point? Right? How do we define a hypothesis function to predict something when we don't know what we're supposed to predict? Right? Or similarly, if we have a new example, I want to form a prediction of that, what does that even mean to form a prediction? Right? There's no targets to our prediction anymore. And the high level is that instead of trying to predict some concrete thing, we're going to instead try to extract some form of structure from the inputs. But we're going to codify that in a way that's very similar to how we explain the supervised learning. So let me sort of describe what that is at a high level, and then we'll jump into some details. So to start off with, I'm going to just state for the time being that virtually all unsupervised algorithms can be interpreted in the following way. Just like before, we have a hypothesis function, or rather they can be formulated in this following way, like supervised algorithms. So remember, we had these three ingredients for a supervised algorithm, right? We had a hypothesis function, a loss function, and a way of optimizing it. And all I'm saying here is that those same exact three ingredients are going to also apply to unsupervised learning. So just like before, we're going to have a hypothesis function. I'll talk about what that means in a second. A loss function, and a way of optimizing this loss function given the hypothesis function, right? And by optimize here, I mean pick parameters for a hypothesis function that minimize the sum of losses over the training set. But what do the loss function and hypothesis function signify in unsupervised learning, right? It's very unclear now, because before we could define a loss where, when you had supervised case, you would think of a loss naturally being something like how close is your prediction, your hypothesis, and the actual output, right? That seems obvious. So, but what do you do in the unsupervised case? So this is where I'll finally get to the point that I've been making so far. But the idea here is actually very simple. So we're going to start with the same thing. We're going to have xi, we're going to have inputs xi in Rn. We're going to have parameters which define our hypothesis function. These are going to be theta in Rk. And here, this is just kind of convention here. Really, what's going to happen, like for decision trees or these more complex classifiers, theta is going to kind of be a proxy for all the parameters that we're going to tune in our algorithm. So it's going to be things like the means that we're going to use for the k-means algorithm. But I'll explain that all in some detail. Just think of it as these are the things that we are actually optimizing our loss function over. So then there's our hypothesis function. And here's the first big difference. So the hypothesis function in unsupervised learning is typically meant to recreate the inputs. So this is a function that takes as inputs just our input vector and produces something which kind of crucially here is in the same space as that. And what we want in unsupervised learning is that we want our hypothesis to approximately recreate the input. So I'm going to talk about what I mean by that in a second. It will become more clear, I think, when I give the two examples of k-means and PCA, how they are both actually doing this exact thing. But this is the idea. And I'll talk about why that's also weird, because, I mean, couldn't you just always set this equal to x, right? Wouldn't that be a pretty good hypothesis function? It should have really low loss then. I'll talk about why you don't want to do that, or why it's not very interesting, right? So why you forbid that, and how you forbid that from happening. Then I'm going to have a loss function. Oh, that should be, oops, that should be, hang on, fix this. This should be Rn. The loss is Rn, Rn. Okay, so I was missing the n's here, because our hypothesis and our actual x are both in Rn. So we have a loss function, which is a function that maps from Rn and Rn to some positive loss. And I think actually the example we'll use all day today is just going to be the loss between the hypothesis and the actual x is just this L2 norm of the difference. Just the Euclidean distance between these two things. And now that we've set this up, we have the exact same kind of canonical machine learning problem as before. Namely, we want to minimize over our parameters the sum from I equals 1 to m, that's the number of data points we have, of this loss of our hypothesis on the training example I and example I. Okay, so that's the framework. And now the nice thing about this is that once we have this framework set up, you sort of know how every algorithm is going to proceed. If we're going to define some hypothesis class, we're going to define a loss function, and then we're going to define how we optimize that. And again, just like in unsupervised learning, in supervised learning, people often will conflate algorithms for hypothesis functions, for all these kind of things that just know what we mean by a full unsupervised algorithm is actually the combination of all those things. So this seems odd. I'll sort of jump in now and say this seems odd, right? This doesn't seem normal, because I've talked about how we want to, predict some output that is just the output of the hypothesis function is just the input to that function, right? Which seems very simple. Why can't we just pick the function h theta of x equals x. Forget about any parameters, right? Just predict what came out of the, predict what was put into the function. That would have zero loss for any loss function, right? Because loss functions measure how far apart things are. Certainly for squared loss, you will have zero loss there, but pretty much any loss, you'd actually have zero loss there as well. So why don't we just do that? And the answer is that we could, but it's not very useful, right? We don't actually learn anything about the data when we do that. And so in particular, what unsupervised learning actually does is it's going to impose restrictions on this function. So we're going to restrict our allowable class of hypotheses to something which actually does not include the identity mapping. Right? So we're going to constrain it to have to make predictions that are in some sense, could not be this complex. It doesn't seem like a complex function, I know, but actually it is a fairly complex function because it can output anything, right? Whereas we're going to restrict it to only output a smaller subset of things. A couple questions now. Yes?
Is it actually the same as the overfitting? Is it complex function?
I don't want to bring, so the question was is this the same as overfitting? You can interpret it the same way. It's a little bit less intuitive this way though, because overfitting kind of seems obvious in the supervised sense, and that you have enough. You're trying to predict something, and you can predict that exactly if you want. And those functions seem complex, like a high-degree polynomial. It seems complex, whereas this function actually seems simple, right? It seems like it's the simplest thing you possibly have, right? It's the identity function. So it's really a different kind of complexity, a different kind of overfitting. So I tend not to use those words, but there are similar themes going on. Yes. Yeah. Why is this useful? Was the question. Where we use this here? This is the entire framework of unsupervised learning. So every algorithm is going to be derivable this way. Every unsupervised learning algorithm you can derive this way.
I'm asking, predicting the input itself, what is the practical application?
I'll get to some unsupervised things in a second, why you might want to do that. The idea with all this is it's going to uncover structure in the data. So if you don't have, I mean, this is sort of the fundamental question, right, is what is the point of doing machine learning when you don't have outputs? And the fundamental idea here, and I guess the goal, oops, I said the goal of Superman, a couple typos in this slides here. The goal of unsupervised learning, fix this as I go. Goal of important difference there, unsupervised learning, is to pick some restricted class of hypothesis functions. And this is sort of the key part maybe. It's that this class will in some sense extract some type of structure from our input. And that type of structure you extract actually depends a lot on the hypothesis you're going to use and sort of how you're going to optimize it. And we'll see two examples of that shortly. But these things are actually very useful in practice in order to be able to describe data, to understand data, and to sort of pre-process data without having to have any sort of target function you're trying to predict. And in particular, we're going to consider, in this lecture, two different algorithms that both fit into this general framework. And that's going to be the k-means algorithm and the principal component analysis algorithm. So, any questions here? K-means I'm going to cover in some detail, whereas principal component analysis, the actual algorithm itself uses a little bit more advanced linear algebra than I wanted to introduce. I think there's plenty of linear algebra already. So I'm going to show you what the PC algorithm does visually more than I'll actually describe it. I will have a slide that sort of describes the algorithm, but it's going to be less important, I think, than the intuition. But for the k-means algorithm, we'll go through it in some detail and actually describe how it works and what it's doing. All right, so let's talk about k-means now. Who here has heard of k-means before or implemented k-means before? OK, so maybe a third or so. So k-means is a great algorithm to start unsupervised learning with because it's very visually kind of appealing and obvious. And here's the basic idea. Given some set of points, and these are our points here, really, right? Our xi's are our points. These are our input data. We want to find k centers in this data. I'm going to call them kind of alternatively. I'm going to alternate between calling them centers or means. That means the same thing as far as the algorithm is concerned. But we're going to find k centers or k means such that every point in our data is close to at least one of them. Okay? And in some sense, if we can find that, then in one way or another, in some sense or another, we've been able to kind of summarize our data, right? Take a lot of data and kind of compress it and say, you know what, these two or these k centers, everything's kind of close to them, so they are a good representation of our data as a whole. So for example, if we have these points here, it's kind of obvious, but I maybe would pick these two centers. So I'd pick one center that kind of is close to all those points, one center that's close to all those points. And the way we sort of view this graphically is we highlight the points by the center that they belong to. The center that they are closest to, they will get the color of that point. OK. Does it make some sort of sense to say that, you know, finding these centers in the data, and I'll show some examples later, but finding centers in the data in some sense or another is kind of providing a summarization of the data, right? Because we have all these points that's sort of complex. Putting those two means up there says, you know what, don't worry about all those points that they have. Just worry about these two means. Those are a sufficient description of most of the data because any point in the data set is pretty close to one of those. Okay, so with that as the motivation now, I want to describe how this fits into that framework of unsupervised learning that I described so far. So let's talk about k-means in the unsupervised learning setting. So for k-means, before we have, remember, I'll just write it again, we have our input xi, where each xi is an n-dimensional point. And we're going to try to find k centers that describe all those points. Oh, no, I should say that I equals here, I equals 1 m. So there's m total points. M should be bigger than k for this to be meaningful. If m is less than k, then you just pick less than or equal to k, then you just pick all the points. That's your summary. But if m is less than k, then you have to provide some sort of trade-offs between picking good points that are close to as many points as they can be, or rather picking a set of points such that every point is covered by some point. Okay, so the way we think about k-means in terms of this framework, this hypothesis function framework, is the following. Well, first of all, our parameters here are just going to be the k different means. So our parameter is theta. Theta is going to be shorthand for the set mu1 to mu k. Right? So again, sorry, I'm using theta here very loosely. It's not really a vector, but it's just a collection of all these parameters, where each one is in the same dimension here as the input. So each one is a point in Rn. And our hypothesis function is actually fairly simple. Our hypothesis for an input x is that we're just going to pick the mean that's closest to that x and output that. Okay? That's our hypothesis function. We're going to find the closest mean and predict that. Now we can't, obviously that does not allow us to choose the identity function, right? We cannot predict any point. We cannot predict points exactly. We have to predict points from some restricted class, which in this case involves all those means. So the hypothesis is going to be equal to, I'm going to write this as the argmin. I think I might have written it before, but argmin just means I actually return the argument that minimized the thing, right? So if I say argmin over mu in this set, mu1 to mu k of mu minus mu x. That just means that I look through my entire set of all my mu k's. I set mu with no superscript to be equal to each of those. And then I find the one that minimizes the distance between that center and x, my input point x. And I just output that center. Okay? And the loss function is just going to be the difference between these two. So when you think about it, all this really is, this is just a formal description of the problem we had before, right? So I said we wanted to find some centers that such that for every point in our data set, we have some center that's close to it, right? And a way of formalizing that is to say, well, I'm going to take my hypothesis function to be outputting the closest center, and then I'm going to measure my error my loss in terms of how far away that is from my original point. So we'll come to an example in a second. It's really a very sort of simple algorithm, but that's the idea. We're predicting from this restricted class of centers, so we can't predict anything. We can't have h of x equals x. And we want to find the centers that minimize these errors. Yeah?
In the loss function, where are you varying to minimize your loss? Is that where you vary k?
Right. So the question is, what are you varying to minimize your loss? So maybe I'll write it down here. So our Yeah. So what are we minimizing here, I think is the question. And what we're minimizing over here are we're not minimizing over k, we're minimizing over the actual centers themselves. So we can pick what those k centers are. So we're minimizing over mu 1 to mu k. Minimizing the sum of the errors, all our errors and all our data points, sum from I equals 1 to m. And I'll just sort of write it, I'll just substitute the loss in here. But h theta xi minus xi, right? Which, by the way, is this is just equal to this thing here. It's just equal to, I'll write it like mu closest at point I. So what we're minimizing is we're minimizing the sum of the distances between the closest mean and the actual data points over all the data points in our training set. And importantly, we're minimizing here over the means. Does this make sense? Yeah. You cannot substitute the term in the third expression from the first expression. Sorry.
So the h term in the third expression is the square distance between the center and the data point.
The h term always means the actual mean itself. It outputs the mean that is closest to that data point. It is the same as you mean this first line here? It is the same as that.
The first expression means the square distance.
So the first expression is, and this is important, the first expression is an argmin. So the argmin returns the argument that minimizes that expression. So the first expression returns the closest mean to x. So it's the same, it's definitely, I'm not changing definitions of h here. It's definitely the same h you have in all cases. Yeah?
So we're copying the norm twice instead of once. Because we could have just done it in the beginning.
Yeah, so this is the mathematical definition of it. This is not how you compute it in practice. In practice, you save those distances and you use them to compute your loss function. We'll talk in a second about how you solve this. You can solve this really quickly, actually. There's some really nice tricks you can do to optimize this thing in very few lines of code, but we'll get to that in a second. Okay, so this is a little bit strange, this notation here, but it's actually, I think it's important because it will get to the heart of this notion of what a hypothesis is in unsupervised learning versus supervised learning. So that comment on the argument is important. The argument operator outputs the argument that minimizes that expression, not the expression itself. All right, so now the question is, how do we go about optimizing this thing? And unlike not all, but most of the supervised methods we saw, simple things typically don't work that well here. So we use gradient descent a lot to optimize our parameters in the supervised setting. But just like, for example, decision trees, this is actually not a easy function to optimize with gradient descent. And the reason is that this argmin operator is actually really hard to take gradients through. You can't really take gradients through that. As you might imagine, basically a little change in the point or in the means themselves can cause very big differences, can assign a whole different cluster or a whole different center to the closest one. So it's not going to be a differentiable function like some other functions are. So it can't take gradients easily of this thing. And even more so, this is a problem because and I'm not going to worry too much about the form here, but this form of problem is what's called a non-convex problem. In other words, there are multiple, and again, I used that term once before. If you aren't familiar with the term convex, don't worry about it. All it means here is there are actually multiple local optima. So there are actually different configurations of means such that you can't move them a little bit and do any better. But if you move them a lot, you will actually do globally better than in terms of minimizing that loss function. So the way we actually optimize this in practice, and I think this is actually a common theme in unsupervised learning. In unsupervised learning, you often need a lot of effort to actually optimize these things. It isn't quite as formulaic as supervised learning, where you just sort of plug in gradient descent. But in the k-means case, there's a very simple algorithm that actually is guaranteed to produce a local optima, even if you cannot say it's going to produce the global optima. And that algorithm, it's sometimes called Lloyd's algorithm, but really it's also just called k-means. K-means, again, just refers to this algorithm. And the idea is very simple. We're going to repeat the following. We're going to first take all our points and find the center that they are closest to. And we're going to essentially assign them to that center. And secondly, we're going to recompute cluster centers to be the mean of all the points assigned to them. So I have a few examples of this in a second. Maybe I'll actually go through the examples before I show the code. But it's a very simple procedure, right? I have a bunch of points. I have some these superscripts, mu1 and mu2. I'm going to take all the points closer to this one. This might be like these or something. Actually, it would just be a line, right? It would be like this set here. And then these may belong to this one, right? So I take those collections of points, and I set my new values to be just the mean of all the values that are closest to that cluster. So I assign this one to be somewhere like there. This one will move there. And this one maybe will move here or something like that. It's just an example. We have some real data in a second. But it's sort of very intuitive. And what that is actually doing is that is actually taking steps in this optimization objective. Right? So we are computing essentially for each point there, which was the minimum that was assigned to. And then saying, now assume that those assignments are fixed. How would I adjust those means to best minimize this function? That actually is assigning them each to be, that's the second step here. That's assigning them each to be the mean of the clusters assigned to it. So you can think actually of this procedure as kind of being a heuristic approach to take steps in that loss function, even though it's not optimizing it exactly. Because the true loss function, of course, when you change the cluster centers, you rechange the assignments. So it's essentially saying, we're going to assume assignments are fixed for a while, re-optimize the centers, now redo the assignments, and iterate that procedure. There's a question over there?
I was wondering how you pick
Yeah, so we'll talk about that in a second, actually, because that's actually a very important point, how you pick clusters to start with. So given a data set, so here's the algorithm, a little bit more formal sense. You're given some data set, and I'll just call it xi for I equals 1 to m, and you're given a number of clusters k. I initialize my K clusters first by just picking random data points in my training set. And those could be, the only restriction there is you shouldn't pick the same one twice. But as long as you sample K different ones, you're probably okay. Though with a big caveat I'll mention in a second. Yeah?
How do you decide what to pick for K?
Great question. I'll talk about that too. The question was, how do you decide what to pick for K, which I'll also talk about. We'll get to that in a second. How you do that. Okay. Now we just repeat this until convergence. We're going to compute for each example point. We're going to compute a cluster assignment, and I'll call that Y. It's kind of like a label, actually. It is not a label. It's not a real prediction, but it's kind of like that, right? It's a discrete number from 1 to K. It says which of the clusters minimized this. Which of the clusters minimized the distance between this point and the cluster centers. Right. And then, so that's what I'm going to do inner step 1. And then in inner step 2, I'm just going to assign the new cluster centers to be the mean of all the points assigned to it. So the way I'm writing that is it's the mean of all xi such that the yi, which was our assignment, equals j for j iterating from 1 to k, the number of clusters. Okay, so let's actually, before I show the code there, let's just talk about how this looks in practice. So here is an illustration of k-means on a very simple synthetic data set that has 3 kind of what I would think of as kind of obvious clusters, right? So this is just 2D data, where there's a bunch of points down here, a bunch of points up there, and a bunch of points up there. Now, when I initialize my means to their first settings, this is just randomly. I pick 3 random points in the data, 3 different random points in the data, and that becomes my first 3 centers. All right. So what I'm doing now is I'm showing by the color code of the points here which center they are closest to. Right. So this green guy's closest to that one, actually. Most of these red guys are closer to that one. The blue ones are up there. Right? And now, I just follow this procedure where I take all the red points and make that center there be the center of those red points, the mean of the red points. I take the blue points and make that one be the mean of the blue points, and the green one's the mean of the green points. And then I get here. It's my next iteration. And so even though I started off with these 2 means in that cluster there, the fact that these ones were also assigned to it and had a little bit less, in total this had more weight than the ones that are in the top left cluster, that kind of pulled the mean down into this set and is kind of leading to the separation you kind of want to see, right? Another step again, we get here. This is just a recomputation of the means given these assignments we saw at the past slide. And I believe now we are actually fixed. The clusters don't change from time to time, and so we've converged. Okay, let's take a look at some code that will do this now. And I'm being a little bit fancy here with some Python tricks, but it's worth seeing that this is actually really just not that much code. So here's the whole k-means algorithm. In this line is splitting over multiple lines here, but we won't worry about that. 5 lines of code or so. So what do we do? So I'm using a couple tricks here, but it's something actually that fancy. So I am, first of all, setting mu to be a random subset of the x's. I'm actually not verifying there that I'm going to get different means or different examples for each of them. But when I have 1,000 data points and I'm sampling k equals 3 or so, it isn't too much of a big deal. If you sample 2 the exact same, by the way, those 2 centers will always be exactly linked, right? Because they're going to have the exact same value in future rounds, unless depending on how you break ties for the assignment. But in sort of math, they'll have the same thing, but it doesn't really matter in practice. And we're actually going to change that assignment in a second anyway. Okay, so next I iterate to some maximum of iterations. In practice, you actually want to terminate also if you converge. So if you actually don't change your assignment from step to step, then your means are not going to change either, and so you're done. You don't need to keep doing anything. But for most large data sets, you actually do not need to iterate until convergence. It's just you're sort of tweaking little things on little boundaries. I'm going to be flipping, 1 point like this point back and forth between 2 clusters, and you're having these weird kind of. You won't have a cycle because this thing actually does decrease the objective every time, but you're going to start doing some really middling stuff that probably isn't that important, and so you do want to actually cap your total number of iterations too. So here I'm just capping total iterations. So now, this next line, I'm computing this distance matrix D. And remember, this is actually the same trick I used before when I talked about radial basis functions. So this little code here, all it does is it computes the pairwise distance between every row of the matrix X and every row of the matrix mu. It does it in one line of code, so you don't need any loops or anything like that. It uses the fact that you can break down these products with a linear algebra sum, or a matrix multiplication here, and it just does that in kind of a nice way. So this is just computing all the distances between the rows of X and the rows of mu. And it's building that in the size of X by the size of mu matrix. Okay. Now I am finding the assignment of each cluster. And the way I do that is I find which element of D, so which of those distances actually is minimized, which index, I'm doing the argument here, so this is the argument operator the same way, which index of the different clusters minimizes this distance. Right, so D here would be actually, I'll just give some examples, but D here would be an M by K matrix. And this function, the argument function, the function in there, just computes which index along this axis minimizes, is the minimum one. So if this is the smallest element, it'll output 0. If this one is the smallest element there, it'll output 1, etc. And then I'm doing my little trick, which Eric mentioned in the tutorial for homework 4. If I want what's called a one-hot encoding, so I want a binary indicator of this, I just take the identity matrix, the I matrix, and take the rows of that corresponding to those indices. And that gives me something that looks like this. 1, 0, 0, 0, 0, 1, 0, 0, etc. I guess this is a 3 by 3, so it would only be 3, but that's the idea. And then this is just basically the math for taking the average according to those that one-hot binary indicator variable. So it's less lines than you might write, but you might write a little bit more verbosely, but just the point is you can write this really fast. It's just not that complex. You can have for loops for all of it too if you want, but Python, it'll be much slower in Python, so it's better to do it this way if you can.
In terms of
Yeah.
dimensions,
Yeah.
this doesn't have any limits on the dimensions, right?
Nope. For any k and any n. Yeah. And for good measure, I'll also just compute what the loss is, in case you want that as well.
And so the C will be the array.
C here is going to be this guy. This is C. So it's not the array. C is the one-hot encoding of the labels.
So mu is the centers.
Mu is going to be, mu is a matrix of centers. So mu here is going to be a matrix that has mu1 in its first row, mu2 in its second row, to mu k. So it's going to be a matrix that is going to be k by m, k by n. Sorry. Okay. So there's a problem with all this. Looks great. Works pretty well a lot of times, but there are problems. And the problem is this problem I mentioned before of local optima. And this is not a theoretical problem. This is not kind of maybe it'll happen. This will happen to you if you run it on any. It won't happen that often on this one. I have to try a few times to get it to work this way, but it will happen on any actual data set. You will find that depending on your random subset of initial points, you will get a different solution. And actually, that's not awful, except for the fact that some solutions are often much better than other ones. So here's what happens if I pick a different set of initial points for my centers. Just random. Again, I have no control over which ones I pick. I can visualize it here, but if I have 100 dimensions, it's much harder to visualize, so it's hard to even know which initial points I picked. So here, I start with these initial points. I adjust my things a little bit. I get this setting here. And then, actually, these move. I don't know why this red point moves a little bit there. That might just be a glitch in the drawing. But anyway, this is the point you get now, and it's basically converged at this point. So I started over here. I had 2 points here, but at this point, they were all sort of a little bit closer to that one. The axes here, by the way, are not quite scaled evenly, so those points actually are, in fact, closer to that point up there than to this point. But when I iterate, what I get is I get this point, this one point, the one standard that kind of covers both these two groups, these two clusters, and then I get 2 other small clusters that break up this thing. And iterating this procedure will just sort of move these about a little bit, and in fact, they will just converge to that, and it won't move after that. So that's the point it is found for my clustering. And the problem here was that I started with these 2 points kind of very close together here, covering this whole, both of these points here covering this cluster, and then 1 point up there covering those 2. And we saw last time you can get out of this sometimes if you happen to have a few more. If this one was a little bit further this way, maybe those points up there would kind of pull it that way, and in a very kind of, I'm just describing it very informally here. But this is sort of a sad thing because all of a sudden now, depending on some random initialization, like did we initialize this thing, this mean here, to be here or up here, that will actually affect pretty majorly what we actually assign as our breakdown of clusters to these points. Right? So that's probably not a good thing. It's not something we actually want. So what do we do about this? And there are a lot of things you can do. But one of the most common, well, first I'll say what you can do. You can do a lot of things. You could, for example, just initialize n, or I shouldn't use n, I've already used n. Initialize p different times and just run the algorithm with p different random initializations. Maybe tracking the loss of each one or something like that and seeing which one does better over time. We'll get to loss in a second and how you think about your loss. But a more common heuristic is something called, which has really, I think, become kind of the standard in recent years. It's something called k-means plus plus. It's a really, and the reason why it's so standard, by the way, is because it's so simple. The idea there is that we're going, instead of just picking our initial centers randomly, we are instead going to actually pick them sequentially, according to some distribution which is not a uniform distribution. Okay? And the basic idea is we're going to pick pi. So this is the probability that we pick the ith data point as our next cluster. Well, actually, maybe let me just run the algorithm itself rather than try to say it and then describe it. Okay, so what k-means plus plus does is actually very simple. We start off the same way. We pick mu1 to be a random sample, some random xi. And now we're going to iterate between all over all j from 2 to k. So I'm going to iterate over all my other clusters. And I'm going to select this cluster to also be a random x. But I'm going to do it with a non-uniform sampling distribution. Right? So I'm going to also randomly sample xj is going to be random. But the probability that we select xi, so I'm calling that pi, which I should probably say something like this. You know, I'll just write it like this. But the probability that mu j equals xi is proportional to the minimum distance between all past cluster centers and that guy. So the minimum, and this is not an argument now, this is actually a minimum. So that's the minimum over all j prime, which is 1 to j prime, which is 1 to j minus 1. So I'm sort of iterating between all the cluster picks so far of xi minus mu j prime. Let's see. Sorry, it's written here, so hopefully that's more legible than my scratches there. Those primes and j's with dots are all hard to write with big chalk. Okay, so that's sort of the mathematical formulation. But what is this actually saying? What it's saying is that every point I'm going to assign some probability that I pick that point to be a new center. And that probability of that point is going to essentially be proportional to how far it is from any other existing center. So in other words, if I have a bunch of points here, and I've picked my center to be right there, and I have one point out here, right? If I use maybe have like, a couple points out here, the point where you still want to cluster out there, but there's a lot more here. If I just sample randomly, chances are I'm going to get 2 points from this cluster right here, right? That's just going to be the odds. It's going to happen. But if I have my first cluster point in there, then I'm going to weight all these things by their distance to the closest cluster, closest center. In other words, these here, which are going to have a much higher distance from this existing center than the points here, are going to have much higher weight in my sampling distribution. So we're going to pick them with much higher weight. It's also called something like, this is a common technique in sampling. It's sometimes also called high dispersion sampling. The idea is you want to get a good coverage of your points, not just pick uniformly according to sort of where the points, according to your uniform distribution over to your points. You also want to include some notion of trying to get a good coverage over the entirety of your data. And I actually don't have any results here, but if you run this on those 3 clusters, you will almost always, it's still random, right? So there's always some probability you're going to get the exact same thing, but you will almost always get 3 points in 3 different clusters. And so if you initialize that a few times, maybe do a random testing with different initializations of the k-means plus heuristic now, you tend to do a lot better. So it almost always will give you kind of a good spread of points. Any questions on that? Yeah.
So how do you actually get the probability distribution?
So probability is proportional to this thing, right? Okay, that's a good point. So I said it's proportional to this thing. So you compute all these distances and then you normalize them to sum to 1. That's a distribution. So yeah. So when I say like proportional to that, I just mean you compute them all and you normalize. It's a case where you're actually computing them all explicitly. You're not leaving any kind of unknown. It's not like they're theoretical here. You compute all these terms and you divide by their sum in order to normalize. You have to compute, and by the way, it's the same exact computation you use to compute distances in k-means itself. It ends up having the complexity of a little bit more than one iteration of k-means. So it's fast to do this, basically. Yeah.
So we can choose like probabilities to be proportional to distances.
Mm-hmm.
We also can do it like to be proportional to some function of the distance.
Yep.
So what is going on in practice?
Yeah. So this isn't squared, importantly too. This isn't squared. And the reason why is that there is some proof that you can show that if you pick this isn't squared, it's kind of the right distribution in some sense, in that it will give you actually, even without k-means afterwards, just that initialization with high probability will give you some low cost, which is bounded by something. Now, whether that's actually relevant or not is unclear, but it tends to work pretty well in practice, and it's simple enough that you don't really want to mess with it, so you just pick distance squared as your measure. Okay, now let's get back to one question here. Someone asked this, is how do we select k? And the sad answer here is that there is no right way to do this. There's no answer. Unlike supervised learning, even cross-validation actually breaks down here. So the reason for that is, so first of all, we have the same kind of effect here before, whereas whereby on my training set, if I look at the sum of my losses, they will typically, modulo random initialization, let's say I, get rid of that. I have the same random seed each time or something like that. But modulo that, having more clusters will always decrease my loss, right? Higher k will decrease my loss because I have more points to spread around my data set. In other words, I can have a smaller distance to all of those. Right? So like training error, training loss in clustering will always go down with a more complex class. The frustrating thing here is that there's no really good analog of testing error. If I evaluate the exact same thing on a holdout set, chances are the same thing happens, right? Because take this, right? Here's one clustering. I kind of want the cluster to give 3 clusters there, right? That's my desired clustering. It looks to me like there's 3 clusters there. If I split this one, though, say down the center, right? I'm going to do better in my training loss, but I'll probably also do better in my test loss too, right? Because it's still just points in space. My distance will probably go down. Until you get to a huge, huge number of points, you're going to keep decreasing your loss until you sort of hit, an insane limit that you don't want. And certainly, testing loss here will give you no notion of the fact that there should be 3 clusters in this data. And so there are things you can do, and there are these heuristics that sort of weight some combination of model complexity and decrease over the previous loss. But really, they're all heuristic, or I think of them as all being heuristic. You can put models on top of them, but that's just kind of post-fitting the models to be telling you what you want to say. The reality is what you should do is you should just plot your loss as a function of k and see where it kind of levels off is the most common thing to do. And it's not going to be a perfect thing either. So there's no good answer here. And when you think about it, that actually kind of is a fundamental problem too, because much like, if I were to say, I want to group this entire class into categories, how many categories are there? Well, it completely depends on what do you mean by categories, right? How are you grouping people? By school, by master's or undergrad, by what? So there's no real notion, and oftentimes the data is ambiguous in terms of what the actual groupings are. So it's just a fact of life that we're going to have to deal with some ambiguity in k. And kind of your best bet in some sense is just to take a plot like this and do kind of the best you can with it. So that's how you pick k. You do it by hand tuning. I should have had this plot on the real data set too. I didn't do that actually. I just have the means on the next data set. But let me show you some real data. So here is what's happening. There we go. Here is examples from the MNIST digit classification data set. So this is actually the problem that 688 worked with on your last homework, right? The one was due last Wednesday. So you were writing a support vector machine to classify these things. This is kind of like this canonical problem in machine learning. Everyone knows about MNIST. But there are 60,000 images. Each are 28 by 28 grayscale images. And they're all of a digit between 0 through 9. so you can think of these, I mean, digits look like 20 by 28 images, but you can think of these things really as points in 768 dimensional space, right? That's 28 by 28. No. What's 28 times 28? 780. 784? Okay. May or may not be the correct answer there, depending on if people are trustworthy. I should know that because I deal with this all the time. I should just know that's what the dimensions are. So what these inputs are then is kind of the entire image, pixels of the image stacked one on top of each other. So they would not look, reasonable as an image, but then the computer doesn't care, right? The computer is just a bunch of pixels, so we're going to represent it as a vector in 784 dimensional space. Okay, so these are some examples of the images, and here are, I just have one plot really, but here are the means. When I run k-means on this data set with 50 different means, I'm going to take those means. So I'm going to take this. So this is I equals 1 to 60,000. I'm going to take this. I'm going to generate 50 examples. So mu j for j equals 1 to k, which is k equals 50. Okay. So what I'm doing is I'm saying, don't worry about all these images. These are all described fairly well by one of the following images, right? So that everything in the data set is close to one of these 50 images. And when I run k-means on these images, this is what I get for the centers. And so it actually looks fairly nice, right? These are sort of smoothed out, nice looking images where the points where the images can differ are a little bit more blurry than others, right? So these things that are blurry here, what that means is that I'm averaging pixels together where, people write a 7. Let's actually find a good example here. Maybe like this one here. So these are mostly 1s, it looks like, but there could be a few 9s in there too, actually. So that's this weird average of like things that look like this, and maybe a few that look like this, and some that look like probably like this, right? So it's probably some weird average of these things. And that averages together to make, the straight part kind of straight, but then those parts kind of blurry because you're averaging multiple pixels together. But for the most part, I can kind of tell what all those should be, right? Those look like actual digits. And they look like kind of nicely smooth written ones. So if you take everyone's kind of bad handwriting and then average them together, you actually get things that look reasonably nice in terms of the images. We'll have some more examples of this in a second. We talk about PCA, but maybe if I can remember and just put it in the slides, I will also look at what does this look like as a function of k here, because that would also be interesting. Question? Yeah. So what I'm doing here is right. So each mu j that I find here is also a vector in 784. So I am taking that vector now, and I am just reconverting it to kind of, a 28 by 28 image by just taking taking 28 by 28 portions and stacking them next to each other to go back to a visual space you can actually interpret. But really, I mean, there's actually no need for the x's to be vectors. They could be matrices too. It's just that's not how the algorithm is set up. But essentially, you can think of this as as 28 by 28 array, and this is in the same space as the original images. Okay, so I probably won't finish through it all, which is okay. But I want to talk a little bit about principal component analysis right now. So this is the second unsupervised algorithm that we're going to use, and again, oftentimes this is sort of set up in a very different way from k-means, right? K-means is talking about clustering, whereas PCA, if you've seen it before, you probably have heard of it. I spell it wrong again. It's crazy because my here we go. Here's the correct correct spelling. It's really bugging me that I had that incorrect spelling in my outline. You may have seen principal component analysis described as a dimensionality reduction algorithm, and oftentimes the connections to something like k-means are not that clear, if there is any connection, right? So I'm going to, likely with k-means, I'm going to first describe PCA graphically. And then I'm going to describe it in terms of this unsupervised learning setting. And hopefully you will see that actually there is not as much difference as you might think. OK. So the idea of PCA, well, this is probably not that important. Who here has seen PCA before? OK. The idea of PCA is that we have some space of our input data. And our input data lies in an n-dimensional space, right? We said that? It's an n-dimensional space. But there's some sense in which it probably isn't really n-dimensional, right? Our space actually, in fact, I actually guarantee you that any subspace you have, higher than 10, you're not even coming close to covering all your possible elements in your space, right? Because actually, R10 is a huge space, and to cover that densely, you need a huge number of points. You're not doing that. Your actual data lies on some very small subset of the points, right? And PCA tries to find the best linear subspace to represent your data. And what that means is, in the 2D setting at least, it's sort of apparent in a data set like this that there is more variation kind of along this direction than there is along this direction, right? So if I look at the data, if I don't care about how it's rotated, if I think about rotating it any way I want to, then I can actually sort of find the axes along which it varies the most, right? So you can say that this data varies the most along this axis here, this one, this sort of rotated axis, and it varies less along this axis. In the actual just x1, x2 space, which is our original components here, they both vary in both, right? Because there's some variation along this dimension, some variation along that dimension. But if I look at sort of any rotated axis, then this one clearly has a lot more variability than this one. So what I can do is I can say, you know what? This sort of variability, all of this variability here, the difference between my points and this axis here doesn't really matter. Maybe it does matter, right? But let's say maybe it doesn't matter. And so I'm going to replace this 2D space with a 1D encoding that just sort of encodes, well, this dimension here, and the projection of those points onto that dimension there. So something like this. Something like that, where now I've compressed my data from being two-dimensional. My hypothesis was that it didn't really matter how the data varied along that other dimension. I'm going to just throw away this axis here and just talk about this one. The other way to think about that is that I am taking each point and representing it as just the closest point along this line here. If I want to think about my original space, that is, I'm kind of approximating it by just saying I'm going to throw out that second axis of variation there. Or I'm using these terms somewhat informally, like axis of variation. I just mean really like what is the axis along which it varies the most. You can be much more formal here, but I'm going to avoid that for the most part for this section. Also because I only have 10 minutes left. All right, so now let's put this in a more formal setting in our same unsupervised setting as before. So PCA, as before, has inputs, everything from before, inputs, xi, has some parameters we'll talk about in a second. But I'm going to talk about my hypothesis class first. So hypothesis function is the following. I'm going to take my data point x. So that x again, in R dimensions, Rn dimensions. I'm going to pre-multiply it by some matrix W. And these names are not standard, by the way. It's just I'm just calling it some matrix W. I could use big theta 1 sometimes, but that just gives you more superscripts. So I'm going to call it W. And W here is a matrix in K, the K by N matrix. All right, so X is an n-dimensional point. W is a K by N matrix. So we know that this product here is an RK. In other words, by doing this multiplication, I've effectively thrown out all the information from X except for K dimensions of it, right? X is n-dimensional, but because this product here is only K dimensional, and I'm assuming, by the way, here that the K is less than N. If it's not, you're not really doing a whole lot with this, if it's more than N. So I'm throwing away some information when I take this product here, because I could not possibly recover general points in Rn after I do that. And then I'm going to now multiply by some other matrix U, where U has the opposite dimensions. U is Rn by K, and U kind of projects back into my original space. I should mention the very top. I'm also going, just out of, for convenience here, before you run PCA, you're supposed to always normalize your data. So PCA is meant to be run on normalized data. In other words, data that has mean, across each feature has mean 0 and variance 1. If you don't do that, you end up having like the mean be the principal axis of variation. So you don't do that. You first normalize it. But from here on out, I'm just going to assume it's normalized and just know you have to do that. I have it in the code about the formula for doing that, but just know that it does have to be normalized here. Okay, so this is my hypothesis class. Hypothesis is oops, I didn't really write it out very well there, but my hypothesis is h theta of x equals u wx, where my parameters here, theta, again, is just shorthand for u and w. The loss function I have is going to be the same. The loss is going to be squared loss as before. And so my minimization problem is, I just left it up here actually. Minimize over theta, in other words, over u and w, of the sum from I equals 1 to m of u, w, xi minus xi. 2 norms squared. Okay, so what's this saying? This is saying that we know that by multiplying by a k-dimensional matrix, I am compressing my data down to k dimensions, right? I no longer have an n-dimensional object. I have a k-dimensional object there. Then I inflate it back up to n dimensions again by multiplying by some other matrix. I so far have not said what those matrices are at all. I'm just leaving them as matrices, right? They can be anything you want. And what I'm saying is that what PCA does is that PCA tries to find the best W and U matrices out of all possible matrices that minimizes this reconstruction error, right? So I compress my data point, I decompress it, and I'm trying to find the set of matrices that do the best job of that, at least in a linear sense. Of course, in general, you could have nonlinear compression and decompression. But here I'm talking about just linear operators that can compress the data. I'm trying to find the best one out of all of those. Does that make sense? Any questions there?
So your final matrix is a K by N matrix?
Final matrix is one K by N matrix and one K N by K matrix. Right, W is K by N.
Like your hypothesis function?
Hypothesis function is a function, right, that takes inputs. It's still just, again, H here is just a mapping from Rn to Rn. So just think of it as my hypothesis is the, I mean, we'll talk in a second about what sort of the individual terms mean, but the hypothesis is just a full, it's just the complete compression, decompression process. So it outputs something that's the same size as my original input, and I want to make that as close as possible to my original input.
So you're reducing dimensions
And then inflating it back up. And I want to say, how do I do the best job of that using linear functions? Yeah.
Is this similar to like an autoencoder?
The question was, is it similar to an autoencoder? Yeah, so an autoencoder, for those that sort of may not know, is a term that actually is most frequent in neural networks, but it basically does the same thing. It sort of has a step that makes it a smaller dimension and then inflates it back up. So yes, you could think of this as a linear autoencoder, but in another sense, the sort of point of autoencoders is usually that they are nonlinear. So yes and no. It's something that's kind of the simplest possible autoencoder in some sense. Yeah.
This setting you care only about the product of the matrices U and W, so actually it's just one matrix and by.
Well, yeah. So maybe I don't know. Do you care about? So right. What happened here? Okay. So of course I could take this matrix here, and I could just build the product, right? Make it n by n. It's going to be a low rank matrix. Typically, I mean, there's no point in forming that product because it's actually more efficient to store it as a low rank product and to do multiplication as a low rank product. So probably want to do that. The other thing is that actually the elements of these matrices themselves are quite important. Because, as we'll see in a second, the actual columns of, for instance, U say something. These are called the principal components of the data. In other words, they kind of tell you these are essentially the axes here. I'll get to that connection in a second. But the point being, you don't want to do that. You actually want to leave your data in these two forms so that you can understand what are the principal components, sort of how are you doing the decompression, and how do you do it in practice. Yeah? Yes. Right. So that's a great question. I didn't have any slides on it, but thinking through the lecture as I was talking, actually, I realized that I probably should put some slides on uses of both k-means and this in supervised learning methods, because they're actually both very useful as pre-processing stuff for supervised learning. Anyway, the question was, I'll just sort of say my take on that, actually. The question was, don't you want to sometimes have the compressed representation of this instead of the full one? And that's absolutely right. You definitely do. So what the practical application of PCA often is that I don't do this full thing. I just do the first product here. The first product gives me a k-dimensional vector that in some sense has to encode kind of most of the information about my original vector, right? So that I can actually inflate it back up. And oftentimes you want to just work directly with that compressed representation. So we're about out of time, so I will have time, fortunately, to put in some extra things on this. But that's absolutely right, is that oftentimes you will want to work with that reduced representation of your function. Now, since I am out of time, and I'll sort of say, visually, kind of this is your x, and then this reduced representation would be just wx here. So this one that we showed in the beginning, that would just be wx. It wouldn't be the whole thing. If I want to then take u, what I would be doing is I would actually be computing the projection of these things onto that vector. So u, wx, would be basically moving these points to the closest point along this line, whereas wx is just that line. That's the picture to keep in mind here for PCA. Now, I'll show the algorithm in a second. But the thing that I actually want to highlight is that this problem here, something kind of amazing happens here. This problem here, like k-means, like decision trees, like all this, is a non-convex problem. we cannot actually, like neural networks, which we'll talk about in a second, they're all non-convex problems, meaning it can have local optima. What's amazing here, though, is that we actually, despite that, we can actually find the globally optimal solutions for U and W using an eigenvalue decomposition, or also a principal, or sorry, or also a singular value decomposition, which are of course related. So I'll talk next time very briefly about that algorithm. I don't want to go into too much detail because I did promise you that inversion was as complex as we would get for linear algebra in this class, and we've already had plenty of linear algebra. So I'm not going to talk too much about SVDs or eigenvalue decompositions, but do know that the amazing thing here is that even though this problem should not be solvable by all sort of rationality, you actually can solve it, and you can find the optimal linear compressor and decompressor, and that really is the PCA algorithm. Okay, see everyone next time.